at was this. Okay, on the, let me go to my modules here. When you go to the gas law notes and packet here, if you click on this, you're going to see that like what to upload. I also need you to upload, and some of you did. I need you to upload the last page of the notes. Okay, it goes with this video. So there's this, and again, you can 1.5 speed it, but please make sure that you watch this video on real gases. Okay, there's a part in there where I have students, and I think I tried to cut it out, but it was taking me too long. So you might hear me ask for students to like answer questions. It's from last year. So just make sure that you remember that the one thing that I've seen on the AP is like, when do real gases play a role? Okay, when does it make a difference that it's a real gas versus an ideal gas? And this is really important because we know that we've been using the ideal gas law, and then all of a sudden we're talking about real gases, okay? And so the difference is that once you get to high pressures or low temperatures, at really high pressures, then what's happening? So imagine like a high pressure system and you have gas molecules, right? So somebody can unmute. What's going to happen when you have high pressure system and the molecules are really being pushed close to each other? What's going to happen?
They'll slow down.
They're going to slow down. And when they slow down, gases could turn into what?
Liquid.
Liquids, perfect. Or if you're at a low temperature, the same thing. That's kind of the big idea of this. And so what I do is I say real happy light, real happy light, real happy light. Real gases are basically at high pressures and low temperatures. That's where there's going to be a change. And so you're supposed to incorporate that change. So make sure you watch that video and you fill in your notes, and then that also gets posted. Okay. All right. This was a Zoom from calculating molecular weight. I don't think you need to, it's just this one that goes with the notes. Everything else you should have done. Okay. So make sure that you post that if you didn't. And then let me take a look at the checklist. Okay. So let me pin myself. Okay. So obviously make sure that you're going to review your gas law notes and packet. You have an equation sheet. You should have an equation sheet printed out. So just make sure that you have that ready to go. If you don't, print it out first. So make sure that you get that printed out today, or I don't want you clicking out of our site. Okay. So, and my recommendation is not to do the test on your phone. Okay. Because you're going to need to upload your work page. So have a page ready to go. That's blank. That says gas law test work page. Okay. Do not plan on working with people. So I've seen people where I actually have had to call them out because I'm like, why are your lips moving? Do not plan on FaceTiming anybody while you're doing this. It's going to waste your time. Okay, I'm going to tell you that first. You're going to run out of time for sure. Okay. If you have to look things up, you're going to run out of time. I'm telling you right now. Okay. This is not a team test. This is a, you did your work. You show me what you know. Okay, so please make sure gas laws are really important. I would rather that you said to me, Mrs. Ismail, I don't know what happened. I would rather take an incomplete right now. I'm going to talk to my parents about it. I'm going to take this next week. I would rather that you did that than you cheat on this. Okay, especially for the sake of like, because gas laws are so important. So please make sure that you do that. And then where are gas laws on this sheet? Why is it sending it over there? Oh, why you just sent it over here? Okay, so if you take a look, there's an old, I did post the old version of the gas section. And the reason why is because like, I'm not going to expect you to actually use this equation. That's going to take forever. The AP doesn't do it either. Okay. What they want to know is when you use the equation, what happens? What are you correcting for? Okay. So I want to make sure that, again, watch that real gases, watch that video, fill in your notes, and then it should be clear. And then this is the gas law section. Okay. So that's the version that you want. All right. So again, maybe you have your phone up with your equation sheet in case you need some to look at some of the equations. and then you're taking the test on a laptop. Okay. Measuring pressure, and then, oh, obviously have a periodic table. Okay. Measuring pressure. So P is force per unit area. How do barometers and manometers work? Again, the way that I always remember it is I always say, is the gas pushing down more? So if on the gas side, and the gas can be on this side or the gas can be on this side, I'm not talking about air pressure. So the air pressure is going to work opposite on an open end manometer. So what you're going to do is you're going to check to see, is the gas pushing down more? What do I mean? It's going to be pushing down on the mercury more. So if the gas pushes down on the mercury and the air side is higher, then that means that you're going to add whatever the air's pressure is to the difference. Okay. Obviously, and then the opposite, if the gas pressure is lower, then the mercury level is going to be higher on the gas side. Then you take your air pressure and you subtract the difference between them. Again, make sure that your units are the same. So if you need to do any converting, that you can do that as well. Okay. So closed end, don't forget. And I've seen questions on the AP, so that means that I may do it too, where it says the atmospheric pressure is blah, 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 and a closed end manometer, you don't care about the atmospheric pressure, okay? So if it's a closed end manometer, all you want is the pressure difference between the two sides. That's it. The air doesn't matter if it's closed, okay? It's vacuum sealed. They've already got that figured out, so that's it, okay. Combined gas law, we know Boyle's, Charles, Gay-Lussac's. When do you use one over the other? I always use combined. I always use combined. I don't use one over the other. I use combined, and then if they don't tell me anything about pressure, well, it's Charles' law, and then I'm just going to cross off pressure, okay? Please, please, please be careful. I've had people like, so you're going to turn in your work page, and I'm like, how did they get this answer? And so what I'll notice is they'll do something like this. Oops. Just enlarge this real quick. They'll do something like this. V1 T1 equals V2 T2, and then they're plugging in their numbers, okay? Wrong, that's not right. Remember, it's V1 over T1 equals V2 over T2. Now, algebraically, don't forget, so if this is a 2 and this is a 6, and let's say this is a 9, okay? And I'm trying to solve for T2, then you're gonna cross multiply. And I always say start where your unknown isn't. So in my calculator, I'm gonna cross multiply, which means I'm gonna do 6 times 9 and then divide by what is attached in your cross multiplication. So divided by 2. And that's the fastest way to do the math, because remember, it's going to be, your time is going to be a factor here when you're doing this. Okay. So yes, there will be probably some of you that don't end up finishing. Okay. So depending on your skill set and, you know, are you going to sit there and have to like multiply and divide and what's your algebra skill set like, right? That kind of plays into it. And knowing those shortcuts, that's going to make a difference. Okay.
This note.
Question.
Yes. So when you're using combined gas law, there was a question on the multiple choice on the gas laws packet, and it gave you moles also. Is that just to like throw you off because you don't use it like at all, or is it just
as long as the number of moles are staying constant, then you're not using moles. Now, this is a great question, Max. Okay, so I want you to remember that it's actually, yes, P1 V1 over T1 equals P2 V2 over T2. But what's really helpful in AP is throwing your moles down here. Okay. Again, if your moles are constant and they don't say you added some gas in or you let some of the gas out or whatever, and the moles, they're not incorporating the moles at all, and you're just doing, pressure or volume, just checking to see what that is, then you ignore your moles, right? But let's say they want the molar volume. If you want the molar volume and you want to see how the molar volume changes, then that's actually volume per mole. That's liters per mole, just like we did in the lab. So you might actually want to use that and solve for V over N. So if you're looking for liters per mole, it might actually be easier to do that. Okay, and maybe your pressure is changing, maybe your temperature is changing. that works as well. So we're just using a ratio, right? So just keeping that in mind too. Good question, really good question. Okay. Convert all your temperatures to Kelvin. Please, please, please don't forget that. Add 273 to all of your Celsius temperatures, then switch it back out if you need to. So one of the questions that that somebody had asked was, if it's asking me for the answer in Celsius and it gives it to me in Celsius, then can I just leave it in Celsius? No, switch it to Kelvin, then switch it back out again, okay? Don't forget to do that. Don't forget, don't mix up your STP and your R values. That happens, okay? And it's a very, very sad situation. And I've had people do it like over and over again. So these are your R values, right? So these are your R values right here. And by the way, on the equation sheet, it doesn't tell you, it gives you 8.314. It gives it to you in joules per Kelvin mole. That is in KPA per Kelvin mole too, okay? So it's the same number, the 8.314. The 62.36 is for torr. Torr, remember, is the same thing as millimeters of mercury. And then the atmosphere is 0.08206. Okay, and you're gonna get, if you use 0.0821, that was another question, is what if I use 62.4 instead? You're gonna get the same answer, like significantly, you're gonna get the same answer because usually we go down to 3 sig figs anyway, okay? So it should be pretty much the same. STP, please don't forget that STP is different. These are your STP values. Obviously temperature is easy, okay? 273 Kelvin or 0 Celsius, but 273 Kelvin is what we're using in our calculations. But the pressure, okay? The other thing to never forget is, what is 22.4? 22.4 liters per mole is at STP. If you have a gas at STP, then yes, it's 22.4 liters per mole. But once you change any of the parameters, it's not 22.4 liters per mole. Again, I'm going to remind you of this. This is where R comes in. Okay, so I don't know if you remember this, but if I use my standard pressure, so let's say it's 1 atmosphere, and I use 22.4 liters per 1 mole, which is at STP. And at STP, I know my temperature is 273 Kelvin. If I multiply 1 times 22.4 divided by 1, 22.4 divided by 273. Oops. 22.4 divided by 273.
0.08205.
Oh, what? So she says it's 0.08205 or 206, right? Which is 0.0821. So that is, which is your R value in atmospheres. So since I use atmospheres there. So remember, this is a ratio. Using PivNert is a ratio. So just wanted to remind you of that. These are the values at STP. Obviously, you can change the pressure. You can use millimeters of mercury, the 760, or you can use the KPA. But just make sure you don't mix that up, like the 101.3 with the 8.314. Okay, so be careful with that. Maybe have it written down. It's on your equation sheet anyway, but maybe just have that so that you don't mess that up. Okay. Okay. Graphs, please make sure that you're familiar with the graphs and the relationships. So we know that we've got a direct relationship when we do volume temperature, when we do pressure temperature, when we do volume moles. These are all going to be directly related. The only time it's not is PV, okay, is pressure volume. So if you inverse, if you do 1 over P or 1 over V, then you're going to get a linear plot. Okay, what was the significance of Charles' law? If they graphed it, when they extrapolated back, which means they didn't actually have this data here, they just worked, they did these, this was the data right here. And you can see that it doesn't matter if you have dinitrogen monoxide, you have carbon dioxide, you have methane, you have helium, it doesn't really matter what the gas is. When they decrease, so they were recording what happens when they decrease the temperature, what happened to the volume, okay? And so obviously this was like a balloon or something where the volume could change, and they were trying to maintain a constant pressure, okay? And constant moles, obviously. When they ended up extrapolating back, they found out that the temperature at 0 Kelvin, which is -273, was where you would get 0 volume. Okay, and so that's kind of the importance of that. Okay, know the relationships. Make sure you don't mess up on those. Okay, so like these are inversely related. So if I hold everything else constant and my pressure goes up, my volume goes down. Okay, I hold everything else constant, my pressure goes up, my temperature should go up. Okay, so remember, everything else should be held constant when you look at these relationships. Otherwise, you need to calculate it. So unless it's like super obvious, then you need to do the calculation. So you need to know Avogadro's law. Avogadro's law is the V over N. Okay, and so what does Avogadro's law state? As long as you're at the same temperature and pressure, equal moles have equal volumes. Okay, and so that's why we use 22.4 liters per mole at STP. But if you're at this any temperature and pressure, as long as you maintain the same temperature and pressure, it doesn't matter what gas you have. Okay, I know I'm saying this like syllables, right? But it doesn't matter what gas you have, as long as you're at the same temperature and pressure, you have equal moles, you have equal volumes. Okay, why is this nice? Again, the reason why this is nice is because you can use a ratio. You can do V over N equals V over N. So just keeping that in mind again. Okay. Ideal gas law we know is Pivner. What does Avogadro's law state? Again, V over N equals V over N. And then gas law stoic. Okay. This is probably where I would say a lot of people mess up, is on gas law stoic. Okay. Anytime that you are changing your substance, okay, anytime you're changing your substance in chem, you need to make sure you're doing stoichiometry. Use your balanced equation to figure out what your mole ratio is, and then you're going to need to make sure that you do that switch. Okay, when can you use 22.4 liters per mole? As long as you're at STP, you can use that. Okay, but if the substance is changing, you want to make sure that you switch, because your like gram and your moles are going to be different if your mole ratio is different. So if they say you produced 24 grams of carbon dioxide, how many grams of oxygen gas did you start with? You're going to need to make sure, and they give you the temperature and they give you the, you're going to need to make sure that you use stoichiometry on something like that. Okay. Okay. I always try Pivner first. And then I say, if I have enough variables, because people will say, okay, what do I do? Do I do the stoichiometry first, or do I do Pivner first? I always try to fill in Pivner. If I have 4 out of the 5 variables, then I'm good. Then I'm good to go. But if I don't have enough variables, then I will do the stoichiometry first, and then plug that into Pivner. Okay. Calculating molecular weight of it, and then always go back to the notes, because I don't want to be like redundant here too. If you want to go back and look that back up again. Calculate molecular weight of a gas from density. Okay. I don't want to forget. Let me just see. Let me see where this is. Okay, I think this is where I want to talk about this too. I don't see it anywhere else. Okay. Whenever you're asked for molecular weight, I want you to check to see if you can do grams, moles, grams over moles, okay? Remember when we were talking before and said, so you have, sorry, let me just check. I have a bunch of remind messages, but they're not coming up right now. Okay, so what you wanna do is you wanna check to see, do I know the grams? Can I figure the grams out? In other words, it might not be as easy as you think. They may not just say you have this many grams of gas. What they might do is say, like in the Dumas method, they might say, you have a flask. Oh, there was a gas law packet problem like this. Okay, like number 24. Oh, this is more of a ratio one. Okay, hold on. Let me see this one right here. What's the molecular weight of the sample? Okay. So remember, all you're gonna need to do now in this one, they give you the grams, okay? And so all you have to do is say, okay, I know the grams, I just need to find out the moles. How do you find the moles? Use Pivner, okay? So as long as you know the pressure, which here's my pressure, I know my volume, there's my volume, and then I know my temperature. And so all I'm gonna do, and I know R, so all I'm gonna do is I have my grams, which is the 8.49, that goes right there. And then I'm gonna divide by my moles, which I'm gonna get my moles by doing N equals PV over RT. And that's gonna go right there for my moles. And then all you're gonna do is divide those two numbers, okay? So I have my grams, I have my moles, I'm gonna divide and get my molar mass. Okay, now, what happens if it's more like the Dumas method like this? It's exactly the same problem. The only thing is, what they're doing is they're gonna say, oh, here's your Erlenmeyer flask by itself, dry, okay? Then they weighed it with the condensate and they got 131.328. Well, if you subtract that, somebody unmute, if you subtract that, what is that giving you?
The grams of
the grams of the gas. Perfect. That's just your grams of the gas. So if you get rid of the flask, so it looks like it's a lot harder of a problem. It's not. It's really easy. Okay. Now you do want to check to see. So sometimes, obviously the temperature they're going to change. Make sure that you switch it to Kelvin. The volume. So this is important too. Notice this. They put it in a 150 milliliter dry flask. Okay. That's not the volume of the flask. Why? Because the flask might read 150 at the top, but there's space. Remember that a gas will take up the entire volume. Oops. The gas will take up the entire volume of its container. So if this is my flask and this is where like 150 is, that's not it. It's actually, I have to account for all of this space too. So what we do is we pour water into the flask, and then we empty it into a graduated cylinder to check to see what the actual volume is, okay? And so that's what this number is right here, is saying that's the volume of the flask, okay? So unless they tell you like that is the complete volume of the flask, then you need to look for that, okay? And then again, you're gonna do the same thing, because once you know the pressure, and you know the temperature, and you know the volume, then you can do N equals PV over RT, and then you know your grams, and so you're just simply gonna do grams, moles, grams over moles, okay? So just keeping that in mind. Okay, questions? Any questions so far?
Are we going to cover, I don't think you've talked about this before, the mole fraction problems?
Yeah, I think it's over here. I think it's down here. I'm pretty sure that it's down. I will double check. Yeah. Okay, so like finding chi. Oh, that's the next thing. It's right here. Okay. Okay, so let's see. Calculate molecular weight of gas from density. Okay, so this is not on the equation sheet. Now you can write it down, obviously, because you're taking this online. I don't want you to, I mean, I want you to like know it. The easiest one to remember is mutts kick dirt over their pee. And so what is this good for? That is molecular weight. So if you know the density, and R is obviously constant, you know the temperature, you know the pressure, then you can calculate it. Now don't forget, what is density? Well, all density is mass per unit volume. That's all it is, okay? And so this is a variation of Pivner's. It's a variation of using Pivner. So instead of using the moles, they'll use the mass, okay? And again, it's the mass of the gas, and the volume is the volume of the entire container, okay? The pressure, why do we use the atmospheric pressure? Because we assume that the gas is going to be at equilibrium with the outside pressure. Unless you're collecting it over water, don't forget, if you're collecting over water, you have to subtract out the water's pressure. I got some really good questions, and I wanted to make sure that I covered this. And the question was basically, okay, I understand that if I've collected, so let's say that I have, you know, some container, and I collected the gas over water, and so the gas is getting collected through like some tube. So I don't know how I want to draw this out, but let's just say that it was collected over water in some tube. And so this is, similar to like what we did when we had the eudiometer. Okay, and then this was being collected over water. Okay, and so then we had the gas inside of here. And then let's say this was like the liquid part here, and it came to equilibrium. Okay, so the question was, okay, I understand that the pressure of the gas, I need to subtract out the water vapor pressure. So if you say the pressure, let's say this is hydrogen inside of here, you would say the pressure of the hydrogen is equal to the pressure of the room, whatever your room pressure is, your atmosphere pressure, minus the pressure of the water. Where do you get this from? You get it from a chart, okay? Just make sure that your units are the same. So if this is in millimeters of mercury, this needs to be in millimeters of mercury before you subtract, okay? So convert before you subtract, don't forget that. Okay, the question was, what about the volume? Do I subtract out the volume? Remember that it doesn't matter what gases I have inside of here, the gas will take up the entire volume of the container. It doesn't matter if I have 5 gases or if I have 10 gases. When I ask you what's the volume of the gas, of any particular gas, it is the volume of the container, okay? So please don't forget that. So there's a difference between when we go to do the pressure versus what is the volume of the gas, okay? So I wanted to make sure that that's kind of a big conceptual idea that I think a lot of AP students like either just never hear that or never put it together, okay? Okay, putting a hole. So remember, a fusion is when you have a tiny hole, the gas is going to effuse out until it reaches equilibrium, okay? So until it reaches equilibrium with whatever its surroundings are, then it's going to keep on coming out, which is why if you have like a tiny, tiny hole in a balloon, that's why, yes, it's going to decrease in size, but then eventually it's going to stop decreasing in size, right? And so it'll reach a point where it's in equilibrium with the surroundings. Okay, and it has to be like a teeny tiny hole, right? Okay, and obviously also, I always think of this as like, let's say that you have an elephant trying to make it through a door versus having, I don't know, something like a cat trying to make it through a door, okay? So if you have a whole bunch of elephants trying to make it through some opening, well, it's gonna take a lot longer for them to make it through, right? Versus the cats are just gonna run right through the door. So the smaller the molecule is, the faster the rate of effusion is going to be, okay? So it will effuse faster. Max, will you remind me of what question you had asked? I believe it was one of the multiple choice questions.
It was on number 10 of the multiple choice. Do you want me to repeat the question?
Oh, I think I got it.
Okay.
Oh, wait, it was 14. It was this one, right?
Oh, that yesterday. Yeah, 14.
Okay, so on this question, it's cooled. And we know that the molecules are going to slow down when they cool, okay? And so, I mean, obviously you can see here what the answer is for number 14, okay? And so the question was, okay, molecular mass of the gas is not going to change, right? You're not going to change your, if you have carbon dioxide, it's going to be 44.01 grams per mole. It's not going to change, okay? And so, yes, the speed is going to, if it's going to cool, you know, it's going to slow down. So that's fine. But what about the distance between the molecules? And so the question was, aren't they going to cool down and then they're going to start like, you know, changing into like coming closer together? And so then shouldn't the distance between the molecules be changing? Unless they tell you that it's converting into liquid, then no, okay? So if it's an ideal gas and it's staying as an ideal gas, the gas is going to take up whatever the volume of the container is, which means they're going to be spread apart as far as they possibly can within the container, okay? So that's not going to change unless you're turning into a liquid. Then it's going to change. And again, that has to do with real gases where like your temperature is so low that it's going to change to a liquid. Okay. Okay. So I wanted to make sure I went over that. All right. Okay. Dalton's law. Dalton's law is very easy. P1 plus P2 plus P3 equals P total. Easy. If you know the total, you can subtract to get the other one. When does Dalton's law become more challenging? When they don't give you the pressure of the gases, when instead they give you the grams of the gases, okay? Or maybe they give you the moles of the gases inside of the container. And they say, inside of this container, I have carbon dioxide and water and oxygen and neon. And then they want to know what the partial pressures are of each one of the gases inside of there, okay? So then what you want to do is you want to convert the grams into moles, okay? And then you're going to find chi. All chi is it's your moles over total moles. It's basically like the percentage, but we're not going to multiply by 100, okay? So it's essentially the fraction of moles in the container, okay? And so once you know that, because the gas's mass has to do with how much pressure is being exerted on it, right? So we're going to convert that to figure out our moles and then over our total moles. Once we know that, then we can multiply by our total pressure to figure out how much is being represented, okay? So again, all you're doing is essentially figuring out the fraction, okay? So which is like a percent of the moles of each one of the gases. And then once you know what the percent is or the fraction is, you don't have to shift your decimal 2 loops back because it's already in that format. So if you say chi is 0.22, what does that mean? So let's say I tell you that chi is 0.22 for carbon dioxide. That means it's 22% carbon dioxide. That's what that means, okay? So when you say, what does that mole fraction mean? It's just what is the percentage of it, but with the decimal shifted already, okay? And so the decimal's already shifted. So if you know the percent, remember all we would do is shift your decimal 2 loops back. If it's a percent multiplied by the total, that's exactly what you're doing here, okay? So once you know your mole fraction, just multiply by the total. Okay, if you have gases with a barrier and you open up the barrier, that's a good one. What's the new pressure? Okay, so I have this on the College Board assignment. I have that in the video there. So please make sure that you watch it because I don't know if we're gonna have time. We have like 10 minutes left here. So I don't know if I'm gonna have time, but I can maybe go through it real quick with you, but really important that you understand this one too, okay? So I just said if the 2 gases are put in the same container as the original, you're just gonna add them, okay? It's pretty easy. But if the gases are in 2 separate containers, you have to calculate your new pressure. And so you're using P1V1 equals P2V2 to calculate that. And then you can add them, or maybe they just want 1 gas, okay? So you can always look back at that on the, what did I say? On the, did I say College Board? On College Board, the College Board assignment. I don't know if I said concept builder. The College Board assignment, there's a video there and it'll be on there. Okay, understand how to calculate pressure of a gas over water. We already talked about this. Kinetic molecular theory. Okay, know the kinetic molecular theory. So I use pair just because it helps me to remember. So that it's made of particles. The collisions are elastic, not inelastic. They are elastic. What does that mean? When they hit, they bounce off of each other. Remember, we know that real gases, like when you talk about real gases, there actually are IMFs. So do all gases really do that? No, but that's part of the theory. That's part of the kinetic molecular theory, okay? And then again, no attractions or repulsions, and so that spells pair, okay? So there are no attractions or repulsions because if they did attract, then the gases are gonna stick and then form liquids, but they're not. They just bounce right off of each other, just like you've seen in those PhET simulations. Huge, 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 same temp, same average kinetic energy, always, okay? So I could say, you have a tree and you have a cup of water and you have, I don't know, a balloon with helium in it. Now I have 2 questions. One, in which one of those, somebody unmute, in which one of those are the molecules moving faster? The tree, the cup of water, or the balloon with helium?
Balloon with helium.
Yes, okay. As far as speed goes, the speed of the one that's in the gaseous phase is going to be faster. Or then what you can even do, if they give you 3 gases, then you want to look at their molecular rate, okay? And the one that has the lightest molecular rate is going to be moving the fastest, all right? But what if I ask you about the average kinetic energy? When we talk average kinetic energy, they are exactly the same. The tree, the cup of water, and the balloon of helium all have the same, as long as they're at the same temperature, their average kinetic energy is the same, period. Okay, so keep that in mind. Are some of the molecules going to be moving faster than others? Yes, but on average, they're going to be the same. So I tried to kind of make a big deal out of that. They're all equal. Okay, Graham's law of diffusion, understand it conceptually. So again, the lighter the molecular weight, the faster. Sometimes it's like an essay question and it doesn't say anything about using Graham's law of diffusion, but you're going to need to apply it. Okay, so if you have two gases and you know you're talking about the speed, or you know you're talking about like maybe one of the containers decreases in size faster than the other one, then you can use Graham's law of diffusion. Again, the one with the higher molecular weight is going to be diffusing slower. That one should be bigger over time. Okay. Make sure you can algebraically solve for rate or molecular weight. Don't forget the square roots. Okay. Please make sure, go back to that video if you need to, but you have to, in order to get rid of square roots, you square both sides. Okay. So let me see if I have time to come back to that too. Okay. Calculate liters per mole of gas if the conditions are not STP. We already talked about this. So this is basically using like that PV over NT equals PV over NT like the lab. Remember, if you're at STP, it's 22.4 liters per mole. You can always use that as your ratio. And then you can solve for V over N if you have a new pressure and a new temperature. You can always figure it out that way. Okay, so you'd plug in, really, you could just plug in your R value on this side. And that works the same way. Okay, root mean square velocity. So the big thing about this is your molar mass has to be in kilograms per mole. Okay, and the reason why is if we use 8.314, which we have to for this equation, the joules per mole Kelvin, a joule is a kilogram times meter squared per second squared. And so in order for our units to cancel out, our mass has to be in kilograms per mole. What does that mean? If your molar mass, let's say, is 14 grams per mole, okay, let's say it's N2, it's 14 grams per mole. Remember, if your unit is getting bigger, your number should be getting smaller. So it's not going to be 14,000, it's going to be 0.014. Did I do that right? Kilograms. Okay, so just make sure that you're switching that correctly. Okay, and then we already talked about this. Make sure you watch the video and the correction factors. What's a good way to study? Obviously, you have all the tools. Okay, I've given you enough work that you're studying from. This was that Dalton's problem that I was telling you where what happens, this is a very popular AP question, by the way. So it says the following gases are all at the same temperature and the following pressures and volumes. After the three are open, what's the approximate pressure inside of the system? So, and it says ignore the small volume. So ignore this area right here, okay? So what most people will want to do is simply just add all of them up and say like, that's the pressure, okay? But what you have to do is you have to account for the fact that now there's a new volume. And so since it's a new volume, your pressure is going to be different for every single one of those, okay? So what you have to do first is figure out what your new pressure is after you change the volume. So you're literally just doing P1V1 equals P2V2 for each one. And again, maybe you only need one of them. Maybe you don't need the total. Maybe you only need the pressure of the neon, okay? So then you would just be doing what's the new pressure of the neon gas, okay? All right, and then I've got some helpful sites that are on here too. Okay, questions?
This is kind of like an unrelated question to the notes, but I submitted like my notes and packet before the Zoom, and I didn't know that you reposted a video with the actual notes. For
Yeah, you can just add it. You can just add it in, no problem.
Okay, because I submitted it just like empty because I had like one blank filled in.
Okay, no problem, no problem.
Okay.
I'm just checking to see if there's anything else like in here in the packet. Let me just go back to the first pages too. There's something on that review sheet, that checklist that I wanted to I feel like I went over almost everything on here. Just make sure you retry. Remember, you have the answers. So just make sure that you retry any of the problems to ensure that you're going to be, it's not just about knowing how to do it, right? It's about being able to do it quickly and correctly too. So if you're going to have to search for things and look for like, oh wait, how did I do that problem? I'm telling you right now, you're going to run out of time. Okay. Oh, this is pretty easy, but like what happens when rate of effusion. Okay, that's what I wanted to show you guys. Okay, let me go to it. I know that some of you may not have finished it, but when I talk ratios, so like number 24, for example. Okay, so in this problem here, it says that the team weighs the bulb and it's 108.11. Move some of this stuff out of the way. So this is the grams of the empty one. So that's our empty. They trapped a gas and then they found it was 110.77. So again, we can subtract those two numbers and then we're going to get our mass. Okay. Then it says using the same glass, the bulb contains carbon dioxide. This is it with CO2. Okay. At the same temperature and pressure. What's the molecular weight of the unknown gas? Okay. So we're going to subtract in both situations, we're going to subtract the empty glass, okay, the empty flask. I don't know, I guess I can do it pretty quickly, but let me just say that I'm just going to make up the numbers. Let's say that this one is about 2. Oh, sorry, my pen's not working. So let's say it's 2 grams. And let's say that this one is, which one's bigger? 2. This is 110 and 108. So let's say it's like 2 point, I'm just gonna make it up again, 2.1 and 2.4, let's just say, okay, grams. And all you're gonna do is you're gonna set up a ratio. So if this is the one for CO2, and I'm looking for the molecular weight of this one, so I'm looking for molecular weights, and on this one, I know the molecular weight of carbon dioxide. So if I know that molecular weight is 44 grams, all I need to do is set up a ratio, okay? And then you're done. Now, again, if you're gonna sit there and try to figure it out and you're not sure what's going on and you're trying to read it and you're not used to the problem, so that's why going back over the problems to see what's happening in this problem is really important, okay? Okay, I think that's it. It's 11:30. The only other thing I was gonna say is just be careful when you're doing an effusion problem, because I will say that one of the biggest mistakes that people will make, it's such an easy equation to use. So you know how it's rate 1 over rate 2 equals square root of like, so you can do A over B or B over A, whichever one that you're doing. Please just be careful with squaring both sides or square root. So just make sure that you're aware of like how to use the equation, okay? Make sure you try it in the problems and make sure that you're getting the right answers, okay? Okay, any questions, you guys? Oh, I think I saw somebody wanted to look at number 13. See if we can just do it over here instead, since that might be a little bit faster. Oops, no, it's not. Okay, so this one is asking you to, so you've got F2 and xenon mixed. The initial pressure of F2 is 8 atmospheres and xenon is 1.7 atmospheres. When all the xenon reacts, forming a solid, the pressure of the unreacted F2 is 4.6 atmospheres. Temperature is constant. What's the formula? Okay, so the way that I like to do this is I like to set it up as like a chemical reaction to see. Like I know that I'm starting with F2 and Xe, and it's going to make some XeF compound. So I know that because I look at my answers anyway, right? And I know it's going to make one of these. So there's one subtraction piece that I need to do because the initial pressure is 8 atmospheres of the F2. After it's done reacting, the unreacted is 4.6. So if I know how much didn't react, then I should be able to figure out how much reacted. And so once I know how much of the F2 reacted, and then I also know how much of the xenon I had, and obviously that's all gone because all the xenon, it says all of the xenon reacts. So that's all gone. That's your limiting reagents. So then I'm looking at it as a 3.4 to 1.7 ratio. So I said it was a 2 to 1. And so if it's a 2 to 1 ratio, then it has to be XeF4 because F2 is diatomic. So a lot of people thought it was XeF2, but because fluorine is diatomic, that's why it would be a 2 to 1 ratio, which would make it XeF4. That's a good question too. Okay, you guys, 11:32. Anything else?
I just had a question for submissions. I know you don't want us to like leave the Canvas site obviously during the test, but in order to submit a photo and we have to like email the photo to our email and like download it, is it
Yes.
okay if you leave it? during
Yes,
that
for sure.
upload?
Yeah. So at that point, that'll be at the end of your test. So what I should see is once you're done, then you're going to do that upload. It's going to be the same as last time. It'll be that last step. And so same as last time, what you shouldn't be doing is like, I see you leave, and then all of a sudden it says, student answered questions 14, 15, and 16 or whatever
Okay.
after leaving. So yeah, so just make sure that's the last thing you do.
Got it.
And don't forget to give yourself time for that. So if people start saying like, oh, I ran out of time. Yes, you're going to run out of time. So please make sure, and I'll let you know as we're in the Zoom too, to give yourself at least 5 minutes to do that upload. Okay. Okay, you guys are awesome. Thank you for being here. Thank you. Thank you.